Good morning. Welcome to Krishna's classroom. We proved the isomorphism theorem related to Hilbert spaces. Okay. So what we have proved so far, we have in fact proved the following. If U alpha is a, so we have proved that if U alpha is a maximal or same as complete orthonormal basis, in a, what do you call this, orthonormal set in a Hilbert space H then and if x hat alpha, inner product of x with u alpha belonging to the x set, then the mapping x to x hat alpha belonging to A is a Hilbert space isomorphism of H we shall just recall the following. So this is a result that we have already proved. Okay. Now U alpha is, if the condition is this, if U alpha is a maximal orthonormal set in the Hilbert space H and x hat alpha is equal to this, then the mapping is, so we have specifically said what exactly is the isomorphism. Okay. Now it's better to recall the following also. What is L2A? Let A be an index set. Okay. Let A be an index set. Let X be X alpha for alpha belonging to the index set A. I am not assuming here A has any specific structure, like it is finite, countable, or it could be even uncountable. Okay, this could be even uncountable. Where of course X alpha belongs to for every alpha. Then we define L2A as the set of all X equal to X alpha such that it's finite. You know that whether A is countable or uncountable, effectively this sum is always a countable sum, a finite or countable sum. Okay, that is X alpha equal to 0 for all but a countably many alpha, and this sum is well defined, and this is the requirement is that we are choosing X to be those X alpha for which this sum is finite. Then you see that L2A is a Hilbert space with inner product conjugate. x, the inner product of x with y is the sum of x alpha y alpha conjugate for alpha belonging to A. And you see that what we have written here is that this is actually norm of which is assumed to be finite. So this is the structure of the space, and this is essentially Hilbert space. That is, it's not only an inner product space, but it's also a complete inner product space. Okay, so what we have asserted here is that in this theorem, given H, so given H and if U alpha is a maximal orthonormal an index set, then H is isomorphic to this is the result that we have proved already. But you see, it is subject to the condition that, see, this theorem is valid. Okay, let me make a remark. Between L to A is subject to the condition that there exists an index set A such that, and orthonormal vectors U alpha for alpha belonging to A such that is a maximal orthonormal. So we have proved the theorem, nearly proved the theorem. In all cases where U alpha, there is an index set A and a corresponding set of orthonormal vectors such that the collection U alpha is a maximal orthonormal set. Okay. The only problem is, only thing that remains to be shown is the following, that in any Hilbert space there exists a complete or maximal orthonormal set. Hence, the isomorphism theorem H is isomorphic to L2A holds good if there exists a complete or maximal orthonormal set of vectors alpha belongs to A. So to prove this theorem, all that remains is that there exists, given H, there exists a maximal orthonormal set. The isomorphism theorem is if we can show that in any Hilbert space there exists a maximal orthonormal set U alpha or alpha belonging to A. So this is the only thing remaining to be. If such a maximal orthonormal set exists, then we know that H is isomorphic to L2A, where A is the corresponding index set. Okay, but what we are not sure at this stage is that given a Hilbert space, does there exist a maximal orthonormal set? Okay, or what you call a complete orthonormal set. Now this is the one that we have here after. Okay, so the task is complete once we prove the existence of a maximal orthonormal set in any given Hilbert space. Okay, so let us prove this, but this needs little bit of work. Okay. Now you know that you can have if you have a non-trivial Hilbert space. I mean, I am excluding that Hilbert space having only the zero element. If you have a non-trivial Hilbert space, there always exists a orthonormal set, a orthonormal set in the Hilbert space. That is easy to see. But it is not clear at the outset that there exists a maximal orthonormal set, in the sense that if you adjoin to this collection of orthonormal vectors, or I'll put it this way, you cannot adjoin to this collection another non-zero normalized vector which is orthogonal to every one of this collection. Okay, only 0 is the only vector which is orthonormal to this collection. So if your collection is, if U alpha is a set with the property that the only vector that is orthogonal to or every element of this collection is the zero vector. So or in other words, I will put it this way. Maximal orthonormal set. U alpha maximal orthonormal set if inner product of U with U alpha equal to 0, equal to 0. Now this is the criteria. That means you cannot find a non-zero vector which is orthogonal to every one of these U alphas. Okay. So this is the criteria that this is a maximal orthonormal set. So what we assert is that, I mean, there are several orthonormal sets that you can set up in H, but whether that set is maximal or not, we do not know. Or given a Hilbert space, does there exist a maximal orthonormal set? If we can prove that given a Hilbert space, there exists a maximal orthonormal set of vectors in H, then we can invoke the previous theorem. It says that H is isomorphic to L2. Okay, so that our isomorphism theorem is complete. So what remains to be shown is that in every Hilbert space there exists a maximal orthonormal set. So it only remains in a Hilbert space there exists a maximal orthonormal. In fact, you see that it's not just one. There may be several maximal orthonormal sets. Okay, in a Hilbert space. Depends on which orthonormal sets you work on. As it's clear. But what is important is that you can exhibit, you can show that there exists a maximal orthonormal set. Okay, so the proof of this theorem is based on what is called the zone's lemma. So we shall prepare the ground for that now. So we have to digress a bit and talk about what are called a partially ordered set and then totally ordered set, and then apply Hausdorff maximality theorem, so on, and then use the Hausdorff maximality theorem to prove the result. Let us see how we. So our task is now clear. In a given Hilbert space, there exists a maximal orthonormal set. This is what we have. Okay, right. So we shall introduce the notion of what is called partially ordered sets. Partially ordered set. A set P is said to be a partially ordered set sometimes it is called a poset. Okay, partially ordered set partially ordered by a binary relation this is a symbol less than or equal to if the following holds. A is less than or equal to B and B less than or equal to C implies this is called transitive. So transitive binary relation. The second property is A is always less than or equal to A for every A, P, and this is what you call reflexivity. C A is less than or equal to B and B less than or equal to A implies This is antisymmetry. That is A less than or equal to B, and B less than or equal to A implies A less than or equal to A is equal to. Okay. So now let us give an example, then it will be clear. Or you call this Px, and with the binary relation less than or equal to given by contained in or equal to. So you have A contained in B. See, if A, B, if, so the first one we will verify, that is A contained in B, B contained in C. Then the second criteria, that is A is always contained in. The third criteria, A is contained in B, B is contained in A, implies A equal to B. In fact, this is equal to A. So, is a partial ordering on the power set Px. Okay. Now, I just want to make a remark, says that remark, we are not assuming, we are not A is contained in B, see, it simply says this. So there could be two sets like this. This is your X. So two subsets. So neither A is contained in B nor B is contained in A. So it is not that given two elements of Px, they are related by the particular relation or the binary relation less than or equal to. That is not required. But if A and B are such that A is contained in B and B is contained in C, then A is contained in C. If A is contained in, is always contained in A is contained in B, B is contained in A, if and only if A equal. Therefore, this is a partial or a partial ordering on the set of all subsets of X. Okay, so that's an example. There are several examples that you give. Now we introduce the idea of total ordering. Totally ordered sets. A subset Q of a partially ordered set P is totally ordered or linearly ordered if every pair belonging to Q satisfies the relation either A less than or equal to B or see, not like this scenario. So here given A and B, you cannot say that A is contained in B or B is contained in A. But you can certainly have a chain of subsets or elements having this particular property. Then you say it is totally ordered. Let us give an example. Example will make it clear. Let script P be the open subsets of R2. Okay. Then what you can say about script P? Script P is a partially ordered set. Is a partially ordered set. With respect to the binary relation contained You can easily see that if A and B are two open sets, and if A, B, C are three open sets, A is contained in B, B is contained in C, then A is contained in C. If A is always contained in A, and if A is contained in B, B is contained in A, and this is possible only if A equal to. So that is clear. Now let us take a totally ordered set. Now let Q consists of all open disks, with center at the origin. That is all concentric circles you take, and the interior of the concentric circles centered around the origin 0, 0. Okay, so this is a typical member of that. Well, let's call this dr, the disk with radius r, open disk with radius r, or you call dr r square. Okay. Zero infinity. They are all open disks. So each dr is an open disk center at the origin. Then you see that this collection is totally ordered. Why is it? Because you see that if you take R1, R2, dr2, okay, right? And this relation, that is, this relation gives a total ordering on this set. Okay, see so this means that either R1 is less than, this is because okay, so dr1 is contained in dr2 or dr2 is contained in dr1. Okay, so that gives the total ordering, right? Now we define what is a maximal totally ordered set. the collection is a maximal totally ordered set. Of script P, where P consists of all subsets of the plane. Okay, right. Or all open subsets of the plane. Right. Why is it so? That is, if any P, if any element of P not in Q is adjoined to Q, then the resulting set is no longer a totally here you see that you take Q, a collection of all open disks with center at origin, then you know that it is totally ordered, and this is also a maximal totally ordered set. Why? Because if you take any subset of R2, any open subset of R2, okay, which is adjoined to this collection, then this particular, the resulting collection would fail to be a totally ordered set. Okay, that's why you say it's a maximal totally ordered subset. Right? I mean, that's obvious. I mean, that's clear. Okay, right. Now let us recall the Hausdorff maximality theorem. That's the next result. And this result is essentially the so-called zones lemma. Okay. What it says is the following. This is the manifestation of the famous zones lemma. Hausdorff maximality. The theorem says that every non-empty partially ordered set contains a maximal totally ordered subset. This is the statement of the theorem. Every non-empty partially ordered set contains a maximal totally ordered subset. Okay, that means given a partially ordered set E, there exists some subset Q such that Q is maximal totally ordered subset. Okay, in fact, it doesn't say that this is the only maximal totally ordered subset. I mean, there are possibly several totally ordered subsets. It all talks about the existence of a totally ordered, a maximal totally ordered subset. Okay, so remark. This is an existence theorem. And not that means in a partially ordered set, there may exist several totally ordered, maximal totally ordered subsets. An example that we have seen is the case of all open disks with center at the origin in a plane. Okay, right. That's a maximal totally ordered subset. And this, of course, the second remark is the first one. This is a manifestation of it would be nice if one looks at the famous zones lemma and what it says, and you see the whole modern mathematics that we do is set on this particular foundation, the so-called zones lemma. I'm not going into the details of that now, and we come back to our problem. Okay, What is our problem? Our problem is to show that in a Hilbert space there exists a maximal orthonormal set. That's what we want to prove. Once that is proved, then you have the corresponding isomorphism theorem. So let us come back to our problem. That is, in any Hilbert space, there exists a maximal orthonormal set. Maximal we prove this using the Hausdorff maximality theorem. Maximality theorem. And specifically applying it to orthonormal subsets. Applied to orthonormal subsets. Okay. We shall recall, if H is a non-trivial Hilbert space, this means there exists U is not equal to 0. Okay. Then there is a non-trivial orthonormal set. That is, take U belonging to H, U is not equal to 0, set V equal to U divided by norm U, then norm V equal to 1. Is a orthonormal subset of H. So every non-trivial Hilbert space contains a orthonormal set. So this is the difference that we make, because if it is non-trivial, then H is not equal to 0, the 0 element. Then, so the meaning of this is that H is not equal to 0, or there exists a U belonging to H such that U not equal to 0. Okay. Thus, every non-trivial Hilbert space contains a orthonormal set, which is essentially the collection or the singleton V whose norm is equal to 1. Okay. So that existence is proved. So we shall prove the following. A maximal orthonormal the consequence of and that is what we are after. We want to show that there exists a complete or a maximal orthonormal set in any non-trivial space. Okay. So we shall prove the following here. Every orthonormal set B in a Hilbert space H is contained in a maximal orthonormal set This is the theorem. Suppose we take any orthonormal set in a Hilbert space, then it is always a part of a maximal orthonormal set. Let's prove this. So once we prove this, let us put all these things together, and you will get that every Hilbert space has a complete or maximal orthonormal set. And that in turn proves that H is isomorphic to L2A for some A. Okay, proof. A subcollection contained in H A is an orthonormal such that B is, you take all orthonormal supersets of the given B. Okay, right? That means we take all orthonormal subsets of the Hilbert space with the property that B is contained in A. Okay, right. Partially order P by the set inclusion. So see, already B is a collection of elements of H, which is orthonormal. Now you are considering all collections of orthonormal sets which contain every element of B in it. And then we impose a partial ordering on this collection. What is the partial ordering? Partial ordering is that A is, or you call A is contained in B. Okay, right? So this containment is, or set inclusion is the partial order. This is a partially ordered set. B is a partially ordered set. Now we observe that B belongs to P. Okay. B is an element of this collection. Right? Hence, non-trivial so what do we have? B is a given partially a given set of orthonormal vectors. Okay. Then we introduce the collection P, which consists of all orthonormal sets which contain B as a subset of that, subcollection of that. Okay. Then partially order P by inclusion. Then you see that P is a non-trivial partially ordered set because at least P is there. That is the reason. we are applying the maximality theorem. Hence, P contains a maximal totally ordered class omega, and B is contained in B is an element of or B is contained in omega. Okay, so this is our statement. So we are going to let S be the union of all omega. B is contained. We claim that S is a maximal so P contains a maximal totally ordered class omega, and S be the union of all members of omega, then B is contained in S, and we claim that S is the maximal orthonormal set that we are after. See, the proof heavily banks on the house of maximality. S A1 and A2. In omega. That's clear. U1 is in some A1 and U2 is in some A2. Then for some A1 and A2 in omega, if U1 and U2 are elements of S. Since omega is totally ordered, what we have is A1 contained in A2, or one of the two things are true. So we'll take one of them and then so if A2 then U1 belongs to now since A2 is orthonormal, we have inner product of equal to 0 if u1 is not equal to u2 and this property is valid. S is an orthonormal set. So we have proved that if you take any two elements of S, say u1 and u2, either inner product of u1 with u2 is 0 or u1 inner product of u1 with u2 is equal to 1, depending on whether u1 is equal to u2 or not. Okay. Now we claim S is maximal. Suppose S is not it is not true. S is not maximal. S is a proper subset of a orthonormal that is a star. This is not equal to a star. This is the situation. A star does not belong to omega. Why? And a star contains omega. We may adjoin a star to omega and still have a total order. Now this is a contradiction to the choice of the maximality of method. And that completes the proof of the theorem. Okay, therefore, there exists a maximal orthonormal set in H which contains any given or a given orthonormal set. Okay. So this completes the proof. Okay. Thus, so we can write this let then H is isomorphic to L2, where A is the index set. This we have defined earlier. That means you take X belonging to H, take an X belonging to H. X is mapped to this is the isomorphism between this. And you know that once you have U alpha as a maximal orthonormal set in H, then this isomorphism establishes the isomorphism between H and L2. Okay, so that completes it. Thank you very much.